रहता, तेरा सही रहता सब है। Good afternoon, good morning for some. We'll get started. Thanks for joining the session. We'll start with a quick mind empowerment technique and we'll get started with this session. In our previous mind power, the ability to be able to concentrate and focus, and we discussed that with as well. So today we want to continue how to identify who gave that way we have on our objectives. This way pauses get more in and instead be a witness to the situation. Uh, Many times we think being a witness in a situation is it's not the right thing. But being a witness does not simply mean anything. You can always contribute and help uh, through good wishes and good thoughts as well. But if it's something that is not our strength and it's not something that's related to us, getting involved in something is a waste of time. For example, if someone is just venting out saying, my boss does this thing and he's always this thing, and they want to vent out and they trust you, and you are getting involved in it, and you're listening to it as well. Anyway, then it's a waste of time, right? You can and tell them, how they can overcome the situation if you have that knowledge. If not, you're just taking that garbage essentially, because it doesn't help you, it doesn't help the other person, and you're just wasting your time. So many witnesses. If you're just a witness and you know, situation, for example, I office on time. If you think you can help the person, could. In this situation, there's nothing that you can do. If you just pass by, then you're indifferent. So, but at least you can give your good wishes to that person, and then you're going to work. So, those best wishes and the good wishes you give uh, don't. It appears many times that they don't help anyone, whether it helps or not. But if you make it as a habit, if you make it as a practice, that you're always wishing others well, then the law of karma kicks in and those best wishes will help you. And when you're in need, you will feel that someone is helping you, although you can't see it. So it's just a good practice that you're helping them, you're giving good wishes. Anytime when you're stuck in traffic and you hear siren of an ambulance, uh, you can't do anything. You're just a witness in the situation, but you can always give best wishes. So, giving best wishes saves you from unnecessarily questions about, oh, what happened, why it happened. It's irrelevant in the situations. All you have to do is be a witness and give your best wishes. That saves your time and energy and helps the other person in an invisible way that you cannot comprehend, the other person cannot comprehend, but still you are a difference. Many times we think, what difference does it make? Whether it makes a difference or not, it will make a difference in your life for sure, because your attitude would always be of helping others. You will be empathetic. You will always be caring, and your nature would be of very helpful nature as well. So that's something which protects you from wasting time. It protects you from unnecessarily getting involved in which you don't need to do anything, but you can always give your best wishes. With that, we will start our fourth session for data architecture, but we'll let's in that 1 minute silence, let's spread our best wishes to the world, because there's so much pain and suffering everywhere, and we can make in our way, our contribution. So we'll take 1 minute and we'll just give best wishes for people who are struggling. They could be struggling to get a job, they must be in physical pain, could be anything, but all we'll do is take that 1 minute to focus, sit in silence, and just give best wishes. Okay, thank you. So we'll get started with our fourth session. Before that, any questions of anyone has, and who would like to volunteer today to revise from what we discussed in last week?
Hi, Dr. Mukesh. Uh, so I was unable to attend the last week's session, but I have gone through the recording and
Okay,
probably
great.
I'll summarize whatever my understanding
Okay,
that.
sounds good, Ashish.
So basically, in the previous sessions, we started with the, what are the databases and why we need and all those things. And in the last session, we probably explored more about type of databases like RDMS, NoSQL, and in-memory databases. And just to summarize that, like RDBMS is a structure with predefined rigid schema or structure. An example of that is Microsoft SQL Server. Then we have second is NoSQL, wherein it has unstructured or semi-structured data. Example of that is MongoDB. Third one is the latest, which we normally call NewSQL, which is in-memory databases. That is for very fast performance, and it has is stored in the RAM. Examples for that is single store and SAP HANA for retail. And probably it was discussed that earlier it was the efficiency database was based on the cost of hardware or disk. But nowadays this infrastructure is very cheap. We need the cost of the efficiency is the performance. Now new age databases are focusing on the performance, and because of big data and real-time analytics and all those things. Then it was discussed about streaming data. It was discussed it's basically broadcaster and consumer based. It's a continuous streaming of data without any stoppage. You're not able to consume or write data from the broadcaster, it will get overwhelmed and it will be lost. So it's a continuous streaming of data and continuous consumption. The further I just explored probably like fast data. We call it data in motion, which is streaming data, and that is somewhat different from big data. in earlier days, it was large amount of data. It was stored. Data was at rest. Nowadays, it's a fast data streaming. We use, create and consume that. Then I also explored that there's nowadays uh, stream data architecture is being used in various situations or scenarios. So it's like, for example, of that is that we use multiple data from IoT sensors, mobile devices, live financial targets, stock uh, feeds, then retail systems. All those things are, and all these different streams are combined and utilizing streaming data architecture. Based on that, whatever the use case of the organization is, that is generated.
Okay, great. That's a great summary, Ashish. Uh, that's really good because the more we revise, the more you'll remember. Does any what second session? So what Ashish summarized extremely well what we did in the third session. Does anyone remember what we covered in the second session? Besides Ashish, because Ashish remembers it as he already explained what it was in the third. Does anyone remember what we covered in the second? Take a guess, at least that way, if you even if you remember one point, that's good enough.
Yeah. So I like to summarize.
Yes, please.
Yeah, we have talked about different types of data, like volume based or varieties of data. According to volume data, there is data, and for the varieties like structured data and unstructured data, and XML, JSON type data is semi-structured data, transactional data, and operational data, analytical data, and dark data. And velocity wise, it is fast data or slow data. And we have talked about ERP system, CRM, and web platform.
Okay, very good. That's really good, Damayanti.
Thank
And we
you.
also talked about master data, right? The importance of master data. Remember what is MDM, full form for MDM?
Master data management.
Yep, that's good. I'm glad we are able to revise everything. Please, it's important that you revise these concepts because there's lots we will be reusing these concepts. So it's very important that you understand them and you're constantly revising it because then when you're giving interviews and when you're talking about it, you'll be very fluent about it. You don't have to think. It'll become a very natural process because you know it, right? We covered in our mind empowerment technique. What are the steps of acquiring knowledge? One is just listening. But whatever you listen today's session, if you don't revise it, 86% of it you will forget. So you're spending 1.5 hours today learning 86% of it, which means more than an hour's worth of learning. You will forget. That's how the human mind works. You will forget it. If you revise what it is within the 24 hours, you will remember 80% of it. Otherwise, 86% will be gone. You just won't remember it. So it's very important then you understand and then you revise it. And then when you do that and when you start then practicing what it is, then that knowledge is yours. No one can take it away from you, and it will become very natural for you to be able to talk about it. And when you reach that stage, you never have to worry about preparing for an interview or giving an interview. Like as you saw, how Ashish was revising the points because he's understood it. He remembered it. So that way, when you give an interview, you'll be able to just talk about it. In general, if you can talk nonstop, like how Ashish was doing as an example, for any topic for 2 minutes, it shows your command that you know this topic well, right? So at least you should be able to talk about any topic related with data for minimum 2 minutes. So that way you come across as knowledgeable. In our first session, we also discussed that each of you will be playing a role. I want to make sure that each session is incrementally contributing in development of your role. So one of the things you'll have to start doing it is start making a CV, because you will become what you think you are. So if you want to become a project manager, then you have to would be related with data. Which use cases you want, I can tell you, but I want you to start thinking it based on what you are observing in the job descriptions. We covered in one of the sessions how to be an ideal and perfect CV, where you're the most desired candidate and they desperately want to interview you. And we covered the techniques on how to write those sentences in CV. So I would strongly start urging you to start thinking about it. Look at the job sentences. Once it's in so that way you already have a CV that you want. You already know what's being asked in the interviews, what's the need for the market, and you're fully prepared, because then the session will help you to achieve that goal of getting a good job. Okay. So Damayanti, any
Yeah,
questions?
your
Yes.
voice is breaking in between for that.
Okay. Thanks for letting me know. Let me just check 1 second. Sorry, I had to rejoin. Is it any better now?
Yeah.
Okay, great. Thanks for
Yes,
letting me
yeah.
know anytime. If it's not good, please do let me know. Okay.
And Mukesh,
Yes.
I would like to
Yes.
add one thing. Uh,
Sure.
Everybody, like
Yes.
you were mentioning that we need to revise it, and
Yes.
then this knowledge is ours. So there are two aspects to it. I would like to share that. First is that you know
Please do. Yeah.
understand it, understand the concept clearly, and you implement it, and you have that skill. And second is to explain it in a better way, or conceptually you are very clear, so that you can do the interview and perform in the interviews, as well as organization level discussions whenever, like, if you are creating data structures and all, data
Yeah.
architecture. So these are two aspects. And one thing I would like to suggest is what I have done is that I wanted to revise it and probably summarize it in the next session. So each one of us can have the target that in the next class I want to explain it. That way you will be preparing yourself to explain it thoroughly, and you will be, like you mentioned. I mean, you can speak it for a couple of minutes and organize that whatever concepts you have learned. One
Yeah.
additional
That's
point
a
is
very
that
good idea.
one additional
Yeah.
point is that besides we discussed a lot of things in the session, you can look from the overview point of view or higher point of view. What are the aspects we have learned today? Like what we learned about the type of databases and their qualities and their examples. So that's the one overview. To know what the higher level you have learned, then you probably trickle down the details. So whatever you can learn. But if you know the higher level overview, then probably you can speak and discuss that. That's the way I have learned.
Well, that's a very good point, Ashish. So, anyone wants to volunteer for next week who will summarize today's session? Because I can tell you, whoever volunteers, you will see yourself that you will benefit the most because retain it, right? That you have to summarize everything in 2 minutes, and then it will become a lot easier. Another way to add to what Ashish is saying, at the end of the session, if any one of you can summarize the points, I can summarize it, but then you will benefit the most if you summarize what you covered today, because that reinforces what you learned today in the hour. Then after 3-4 hours, it will still go on in your mind. And this is something called as reinforcement learning, which we use as an algorithm in neural networks and so on. But essentially, it's doing something very similar. Wherever it's training that neural network, it keeps training it again in a way. So your brain is nothing but a neural network. The neural networks are designed based on how the brain works because your brain has neurons, and each neuron is connected with multiple thousands of neurons. An artificial neural network is just mimicking how the neurons in the brain work. So the more you reinforce that information by repeating to it, it just creates those connections between the neurons stronger, and then you will remember it as well. So to extend to what Ashish is saying, at the end of the session, I need one volunteer who will summarize what we covered today. And it could be multiple volunteers because there are so many points. One can summarize what we covered today. Another can cover what the first presenter missed in covering the points. That way, we are sure at least 2 people will benefit from today's session. And then the next week, we want a third one who will summarize what we did today. If we do it this way, you will remember it. You can ask Anita, you can ask Ashish, because they take notes, they revise it, and they can tell you, what we covered it, because they're constantly revising and they'll remember it. So who would like to volunteer today?
I would like to do.
Okay, great. And thank you. That's Damayanti, right?
Yes.
Okay, thank you. Okay, let's get started. So I sent out a poll this week, and question was, can SQL be used for NoSQL databases? And you can saw, right, those who participated the session answered it right. But those who didn't participate it answered it yes. We discussed last week. You cannot just write a SQL query for MongoDB. It just doesn't work. In fact, to take it even further, we also discussed there's no standardized language equivalent to an ANSI SQL for RDBMS. There's no standardized default language that will work across multiple NoSQL type of databases, whether it's MongoDB, whether it's Cassandra, whether it's Redis, and so on. Each one has its own language. So, that's how it is. They don't have a consortium to make it standard. But the good thing is, many of them are like SQL. They are SQL-like, which means if you know SQL, picking up that language is very easy. It takes less time, but it is not SQL. You cannot just take a SQL query on an RDBMS and run it on a NoSQL database, because the structure of the data is different. You're not necessarily defining the structure at the time of the design as well. We discussed last week, like in RDBMS, the first thing you have to do is you have to define the table structure. You have to define the number of columns, and you have to define the data type for each of those columns. Without that, you cannot even create a table. And once you create a table, every time you insert a row in that table, it's validating against it. So that's why when you write a query, it's easier to write the query because you know that whatever you're writing will have that structure. In a NoSQL, it's schema-less. You don't have to define the number of columns or even the data type for it. So writing queries becomes very challenging at times, and defining the structure of the table is equally challenging. But it helps for users. For example, we discussed streaming data or fast data. When you're just dumping the data, and then you want to query it. So usually a good practice is that when you're defining and creating your table in a NoSQL database, you want to create the table which is write efficient, so you can write it. But when you want to create a query for it, you define a table which is query efficient, and it is very much normal and a perfectly a good practice. Like if you have 3 different type of queries and those queries are very different, take a copy of that data and put it in a structure which is query efficient. So if you have 3 different type of queries, you take a copy of the data and you create a table and then write 3 different type of queries, but those 3 different type of queries are referring to 3 different tables. And they are getting that data from this other table in which you're just dumping the data. So it's perfectly normal and okay to do that. We'll cover that more in detail, but I just wanted to start throwing concepts that in SQL, when you're in RDBMS, you're writing your data in one place, you're querying it, and whereas in NoSQL, your table structure is dependent on the query. So you design it in such a way so that it's very friendly for query, because the structure could vary. I want to query my data in a different way, person wants to query in a different way. They both will have different structures to support their query. And another question during the poll was, examples of streaming data. And everyone clicked on stock market news as an example, but the others were like not streaming data, but actually they are streaming data. So I want to emphasize again what is streaming data and how it works. So in streaming data, you're creating the data using some sensor, or you can be just generating data. For example, a live music concert. You're streaming a live music concert. So the person is performing live, and you're generating that data. Remote patient monitoring, the ECG, the blood pressure, it's constantly monitoring that, right? The ECG is changing every second. So it's generating, that sensor is generating that data almost every second. Weather is changing, right? Temperature doesn't remain 33 degrees throughout the day. It fluctuates during the day. Now you can define a time window for that change. You can collect that weather data every minute, or you can collect it every 15 minutes, but it's constantly changing. Similarly, stock market news is being changing, right? One company is acquiring another one. Their stock value is constantly going up and down. It's changing. So for streaming data, one of the characteristics is that your data is continuously changing. But the most important characteristic for streaming data is that whoever is consuming that data is just tuning into that data or subscribing to that data. So they're not pretty much doing a pull, but they're the consumer. The data producer is pushing data to the consumer. You're not pulling. The consumer is not pulling data from the producer, but pretty much the producer is pushing data to the consumer. So for example, in the live music concert, you're just opening a YouTube channel and you start watching that live music. So you subscribing to that channel and you're listening to it, right? So your machine acts as a client, and that client is connecting to that YouTube server, and you're able to see the data. But you're not the only one. There could be thousands other watching it. Each of those viewer is a client connecting to the server and getting that data. Similarly, you can have a RSS news feed, and you can subscribe to stock market news. Similarly, for that remote patient monitoring, there is one station which is looking at the remote monitoring data for all multiple different patients. And there could be AI machine learning algorithms which are constantly looking for anomalies. And what is important is that you're minimizing the delay from where the data is generated and where the data is consumed. And why that is important? A good example is the remote patient. If I'm going to send my data with a delay of 15 minutes and have an algorithm which is looking for any anomaly in the ECG, but this person had an anomaly and we received after 15 minutes, and probably that person has died, right? Very much possible. So we want to send that data as soon as it's generated. So for streaming data, The data is being generated constantly, right? So it's past data, it's changing. And then as soon as it's generated it, you're pushing it to the consumer. So that's what streaming data is. So from that perspective, whether it's the stock market news, whether it's the remote patient monitoring, or whether it's weather data or live music, they're all streaming data sources. Okay. So last week we also talked about, some of you or a few of you wanting to install any database so you can actually practice creating a table. We discussed, right, why it has a data type and creating a table to be able to run a simple SQL query. So I was wondering if anyone who's not been able to do so, or if you're running into any issues or any problems, then we can certainly help you. Or those who already know, it seems like one or two of you already know how to write queries, then that's good enough. But does anyone need any help with the databases? So that way, what we want to, whether it's today or the next one, we want to be able to, I want you to show me how you're creating a table, and we will write a simple query, but you will be writing the query. Because when I'm writing it, I'll do it a lot faster because I know it. I want to make sure you're writing it. You will get errors. That's perfectly normal, because the error that you will get, others will probably be getting the same error. So we'll take some time to create a table and write a SQL query. If any of you is ready, we can do it now, but I want to make sure you or others are also able to follow it and do the table at the same time. If you're not ready, we'll cover some of the more theory concepts. So is everyone able to download a database, or do you want to do it next week? And it'll be very simple, so you don't have to it. All you have to do is download MySQL, and it comes with sample data, but we'll create a database schema which will define structure of a table, and we'll create a simple table and insert some records in it.
Prefer if you wait for one more week so we all have time to catch up.
Okay, sure, no problem. Yeah, that's good enough.
I'm speaking for myself. I don't know what others want.
Probably others would want the same. So you're brave to be able to speak. So I'm assuming it will be the same for others, because based on the poll, I got few responses. So I'm assuming it's the same for others. But it's perfectly fine. We can certainly do it next week. But please do it by next week. And even if you're not looking for a job of a data architect and is this project manager, you're testing it, it will definitely help you and give you a lot of confidence. Because again, we have to follow the 2-minute rule. So if the interviewer asks, do you know SQL? I want you to be able to talk about 2 minutes, right? Just 2 minutes, because that will project confidence. Even if you haven't written a lot of SQL queries, but you can, if you write just one SQL query, you'll be able to talk about it for 2 minutes at least, because that shows you're knowledgeable. You may not be an expert. If you can talk about it for 10 plus minutes, then you're an expert. 5 minutes, which means, you're fairly good. 10 plus means, you really know SQL well. But 2 minute means, that you're not ignorant, you know something about it, and, you come across as knowledgeable. So if you follow that 2-minute rule, it works all the time. So I want all of you, whether you're project manager, whether you're tester, whether you're playing the role of any other role as well, be able to talk about SQL for 2 minutes. Okay. Moving on, I wanted to build and continue on the concepts, because there are a few concepts left between RDBMS and NoSQL. And those concepts will help build on cover next session. So one of the concepts we covered last time was that we use streaming data is used in NoSQL versus RDBMS, because you're not doing a validation of the data type in NoSQL. That's why you can write faster in a NoSQL database. Okay. One of the other different concept was we covered the example of finding one bad orange in thousands of oranges, right? And we discussed that in order to make that search faster, you create a crate with 1,000 oranges, you create it into 10 different crates, right? 100, 100, 100. And you have 10 people finding out that bad orange. In a sense, you're distributing your data, and then you're running a query on it. So that way, with distributed processing, you can get a better performance. We also talked about efficiency. So 20 years back, efficiency in databases was you're using less data space, you're minimizing on the cost of the data storage to store the data and then query it. Now it's about performance. How many milliseconds less does it take to write that query when you're using one database versus the other? Because everything needs to be real time, right? So we covered those as well. One important concept that I want to cover today is that in a database, when the journey started, with Oracle and other databases, you are storing data in the database, right? And then the database has two components to it. One is data storage. You're inserting record in a database table. So you're inserting that data in the database. And then you're using a SQL query to query the data. Similarly, in a NoSQL database, you are inserting or writing the data in the data, but when it's writing it, it's determining in which partition to put the data. But you're still storing the data in the database. You're using a query engine to query the data. And depending, if the query engine, if it supports ANSI SQL, you can pretty much lift and shift that query, copy that data in a different database software by a different software company. But if it's not ANSI SQL compliant or supporting it, then you have to rewrite the query and you have to move that data. But essentially, you are storing data in the database and running a query on it. That's how databases work. There's a fundamental problem with that. And the problem is there are so many use cases where you're writing data in it, right? Like streaming data is a good example. You're writing a lot of this data in it. But not all of this data is being queried at the same time, right? Or some of it is being queried. Especially streaming data, right? You're writing weather data every second. You're collecting stock market values every second. You're collecting patient data every second, and so on. But you may or may not be querying that data. And if you start querying it, right, you are going to have to get more disk space because as the volume of data increases, right, on how you're storing the data, like in a NoSQL, you have to add more nodes in a server. So, and if it's RDBMS, then pretty much, you have to buy a bigger hardware server so you can keep storing more data on it, and then you can reset. Right? So I'll introduce a new terminology today. And may have introduced in the past, but I'll repeat it again. So when it comes to distributed computing, we use the word cluster and nodes. In simple English, a cluster is nothing but a combination of different servers. So one server is like one physical server, right? We discussed last time, right? It could be a physical server which has like 1 TB RAM and, and so on. But you can virtualize it, and that virtual machine could have 4 CPU cores or 8 CPU cores, 16 GB RAM, and you can create 20 virtual machines on one physical server. But that's and then we install the software, database software on that server. So in a distributed computing, you have multiple servers. Each server could be a physical machine or a virtual machine, but you're connecting these different virtual machines. Most of the time it's a virtual machine. You're connecting these different virtual machines, and this group of virtual machines is called as a cluster. Cluster is nothing but, grouping of things together. So you're connecting different virtual machines together, and we call it as a cluster. And each node is a server in the cluster. So you have when you say 3-node server, which means it has 3 nodes in that cluster. Right? Why is this relevant and important is because as your data grows, you can keep on adding more nodes in the cluster, right? So that's called as horizontally scalable. I think in one of the sessions we covered scalability in the data analysis. Does anyone remember what are the 2 different types? How do we do scalability? what is horizontal scalability and vertical scalability? Does anyone remember that?
Yes, Mukesh. So horizontal scalability is like, scaling your hardware or your capacity horizontally by adding multiple nodes or multiple servers. And there is vertical scalability, wherein you are increasing your servers hardware with more or more like RAM or disk space.
Yeah, perfect. So another good way to example to remember, this is how I remember it. Every time I think of vertical scaling, an image of Burj Khalifa comes in front of my mind because that's vertical scaling. You're adding more floors, right? So you're adding more CPU RAM to your server. Horizontal scaling is if you look at any apartment complex in Delhi, you'll see like multiple buildings. If you want to add more capacity, more housing, you just add another building, right? So that's horizontal scaling. So horizontal scaling, exactly like Ashish said, we are adding more nodes in that cluster, thereby adding more capacity. Whereas in vertical scaling, you're just adding more CPU RAM, but there's limits on how much you can add. Just like, once your Burj Khalifa is built and designed, there's limits on how much more you can add to it because your foundation should support it. Similarly, in your computer, there's a motherboard. The motherboard has an address board and it has fixed slots on it. So that's why when you're buying a laptop, it will tell you what's the maximum amount of memory you can add to it. And you cannot add more than that maximum amount because that motherboard can only handle so much. So there are limits on you can vertically scale. But when it comes to horizontal scalability, it's limitless. You can add thousands of nodes. So this is a very important concept, and we'll cover this again in big data. How and why horizontal scalability is achieved. But in general, as an architect, if anyone says, have you thought about or have you designed systems which are highly scalable? And the answer is yes. I've designed systems which are highly scalable by using distributed computing and creating clusters with multiple nodes in it. That will come out as a perfect answer because horizontal scaling is anytime preferred over vertical scaling. Why is this relevant to what we are talking about? Because as the amount of data grows, and data is growing every second, data is growing every minute, with some of these use cases, especially if you have streaming data, even with transactional data, data is happening, people are making purchases over online, over store. So in our fictitious retail company, we started our journey with Excel. We realized, we want to grow our business. We started using a database. And now with business growing as well, more and more transactions are being written in it. There will be some point where there's limits on how much disk space my existing server has for me to insert the transactional data in a database. And I can add more disk space as well, but there's still limits on how much disk space I can add. So one option is I get a bigger server with a lot of disk space, or I can just add more disk space. But then again, there are limits to it as well. For example, I'm buying a hard disk. I can buy hard disk with 5 TB, but I can't buy a 500 terabyte hard disk. Whereas with horizontal scalability, I can go petabytes, not a problem, because I don't have to buy expensive hardware. I can buy cheap hardware and add more nodes to it. So that's why horizontal scalability is preferred over vertical scaling because no limits. I don't have to plan ahead 6 months, 1 year in advance. Because in one of the examples, do we have Dinesh on the call? Probably not. In one of the examples, we said, right, we've got business, and business doesn't want to invest a lot in IT unless they have to. There's a fixed budget for IT. So if you are an architect and saying, I want to build a system, but you're adding too much RAM and too much disk space to your database because your business will grow and you will need that in 3 years. But business says, my business is not grown in that. 3 years is a long time. I can't wait. Why should I spend X amount of money for this database for which will happen something after 3 years? I don't want to invest in it. So if you were horizontally scaling, you can incrementally add it because it's very easy to add more nodes in a server. So you can plan for just like maybe 1 year. And after next year, you'll be like, okay, no problem. I'll just add more nodes in the server. So my design is scalable, which means I can scale to the operations of the business and be able to manage the demand. And I can do it in a horizontal way. So that's why we prefer horizontal scaling. So now when your data is being constantly being added, and if you're storing the data in the database, so your database server needs to grow in size so that it can not only handle that additional data storage, but then you can query it as well. That's a problem statement. So you can use a NoSQL database, which is horizontally scalable, or you can buy a bigger box and you can store it in an RDBMS. Now, one of the questions that comes up in the mind is, I'm talking about horizontally scalability for NoSQL databases. Can I horizontally scale RDBMS? Take a guess.
Technically, yes, you should be able to upgrade anything.
Yes, but it's been a challenge to do though. And the fundamental reason why it's challenging to do that is because if you're horizontally scaling your RDBMS, then essentially you're partitioning your data, and usually it's a good practice because your server could fail in that cluster. So if there's one failure in that node, if one node goes down in a cluster, then your query won't be able to give you the good data because your node went down. So you will get incorrect results, or you won't get all the data. So usually a good practice is you create redundancy anytime you're creating cluster, and you create multiple copies of the data, and you distribute it across nodes in the cluster. So if one node goes down, you still have a copy of it on the other nodes. And NoSQL databases do exactly the same thing. But when it comes to relational databases, it's a challenge to do that. And that's why fundamental architecture doesn't support it. And the reason why it's a challenge to do that for RDBMS and why it's not a challenge to do for NoSQL databases comes to one specific property that's expected out of relational databases. And that's called as ACID compliance. ACID stands for atomicity, consistency, durability. I'll have to Google for it. But I'll explain in simple words what it means is anytime you are inserting the data in the database, you have to make sure you can roll back that as well. And anytime you're inserting it, you need that guarantee that that insertion was successful. That is the key property for RDBMS, is that anytime you insert data in the database, it was successfully able to insert that data in the database. And if it did not, then at least that it's not able to do that. Especially if you are inserting a data in multiple tables, and you need the rollback feature that if it didn't insert into one, it's not able to insert in the other one as well. So that's called as a rollback. So ACID basically corresponds to where you are essentially guaranteeing that your data is available, and if it is executing, if there's any error in it, you are able to roll back that feature. And in to achieve that ACID compliance, right, we'll say a database is ACID compliant if it can guarantee that this data is inserted. And when you are running a query on it, you will get a consistent response. It's not that one time you will get 30 rows for that same query, and next time when you row it, you'll give 20 because one node went down in the cluster. Then we can't call it as ACID compliant because you're not getting that consistency in the results. For NoSQL, we waive that as a requirement. And that allows us to scale the databases as well. And remember now, it's isolation. So atomicity, consistency, isolation, and durability. They sound very complex, but even if you take away the concept in an easy to understand manner, we've achieved the objective for today. Because these concepts, they sound very complex, but if you understand them, they are not. And we'll revise it as well. When you are inserting data in a database, right, you want to make sure that query is giving you a consistent response. So if you are, let's say, if my node in the server goes down, then, I wouldn't get that consistency. So I need to make multiple copies of that data and be sure, there's consistency. So that I can do it. But the problem is I'm writing in a NoSQL databases, right? I'm writing so fast, right? That when I'm running the query, at the time of writing that query, that streaming data is writing somewhere. So when I write that same query and execute it after a few seconds, I'm going to get more data because the data at the time of write was still writing to the other nodes in the database. So you'll say, why is that a problem? It's a problem because to achieve that consistency and have that redundancy, I not only have to write data in a node in a database in the cluster, but I need to write it in multiple nodes in the cluster. Because we said, right, if you store all your data in one node, and if that node goes down, then you lost your data. So I need to make 3 copies of my data. Usually we make 3 copies. When you're writing in a NoSQL database, you're first writing in one node and need to write in the other 2. So if I write it in one node and I run a query, I will get that data. But if I execute that same query within the next few milliseconds, and if it hasn't written that second copy somewhere else, I won't get the same number of rows. So that becomes a problem. So that's why most of the NoSQL databases, they're not ACID compliant because you won't get that consistency when you're running the same query on that same database, you'll get different results because it hasn't written all that data. All the copies of the data have been written across the nodes. So there could be some variation. So the term we use for NoSQL databases is eventual consistency. So when you're placing an order, it wrote it in one node, but then the software, the database software has the provision to make a copy in the other 2 nodes as well. And that way, when it runs that query after 5 minutes, that copy in the other nodes has been made and it will give you a consistent response. So it eventually gave you that consistency, but not in that sub-millisecond, right? So usually the times we will say, who cares? I will query the data few seconds after I've written it and shouldn't be a problem. And most of the times it's not a problem. So eventual consistency is okay. But when RDBMS were designed and written 20 years back, they were designed with that concept that, whatever you're writing is consistent right away because they didn't have this concept of distributed nature where you have to have multiple copies and make 3 copies and do it. They weren't designed that way. So all your data is in one place. Once the data is written, it's validated that it's written and you query it, you will get a consistent response because it's not distributed in nature. It's all in one place. So your consistency will be there. And if you need to roll back for any reason, right, let's say, you're writing data in 3 tables. You're taking a person's first name, last name. You're taking the order details, which goes in a different table. And then, you're sending that order to your shipment, but you're writing that data, which you're capturing in a form, person's details, order details, and the delivery information, 3 pieces of information, all on a web page. When you hit submit, it needs to store it in 3 different tables. But if one of those doesn't get submitted, right, it's didn't successfully place. For example, you place the person's demographic information in the table, You place the order information, but the shipment information, that query failed because, there's some error happened. Some error happened because there was a problem with the database, or some error happened because, this data was not good enough. The shipping address wasn't a valid address. So if it's ACID compliant, it will fail the entire transaction. It will say, sorry, order not successfully submitted, because even those two pieces were correct, but the third one was not. It will roll back, and it's a feature of these RDBMSs. It will remove that entry even after inserting it. It inserted the person's name, it inserted the order details, but the shipping it wasn't able to insert in it. It will roll back the entire transaction. And that way, you're saying order not successfully completed, because all those three pieces are critical. I know who the person is, I know what they're ordering, but I can't ship it. So the order successfully didn't go through it. So that's how they were designed. And this ACID property was a key property to make sure that you've got consistency in your data, and it's atomic. Atomic means it either the whole entire transaction set occurs or it doesn't occur. There's no ambiguity about it. If you don't have all the information related to a transaction, you either commit to the transaction or you don't. So it's atomic. It's either doing it or it's not doing it. It's not partial, where it's collecting one piece of information, it's collecting the other piece of information, and the third, it's not doing it. Nowadays, we give less importance to ACID, and we do something called as microservice. We'll say it's okay to do it. If I don't have the shipping information, it's okay. Collect the person's name, collect the order details, and then when I run a query, I'll know there's some problem with the shipping. That's okay. I will contact the person, and I'll fill in those missing details. But at least I didn't lose a potential sale, because I'm losing money if I missed it out. So now our way of thinking on how much information we want to collect and how we want to process it has evolved, right? So, and then we'll tell you, there's an error with your order processing, please contact us, or, can you resubmit this information? So it doesn't stop you from sending the information, but you can build and design it where you can even collect partial information as well. So the key part is, in an RDBMS, you have that atomicity. Either you conduct that transaction, all or nothing. So atomicity in simple words means all or nothing. You collect all the information, you insert it, or if one piece doesn't fit in, you don't have the right structure for that data, you roll back everything. Consistency is where, after inserting the data, if I run the query, I will get the same response. Whether I run that query 2 seconds after writing that data or 20 minutes after writing the data, I will get the same response. In NoSQL databases, you get eventual consistency. So just after writing the data, if I could get different results, and if I run a query after 10 minutes, I could get a different results. The reason is because that data was not written across all partitions. So when I'm running the query, it may not query the node in that cluster which has the data. So it gives a different response. Next time when I run it, it runs a query and it has the data across those partitions. So now it gives the different results. So even after data is written, depending when that data is replicated across all the nodes in that server, I will get that consistency. But the few microseconds it takes to make copies of that data from one node to the other replicas in that node, for that time duration, there's no consistency. That's why we say NoSQL databases are usually not ACID compliant, right? Because there's that small window during which it may not be consistent. But and most of them previously, NoSQL databases didn't support rollback feature, but now they are supporting it as well. So MongoDB 2 years back didn't do it. Now they have a concept of a transaction, and you can support it as well. So things are evolving fast, but essentially, those are the fundamental differences. So what happens is, it pretty much says all your data needs to be in one place. Otherwise, it's not going to be, it's eventually consistent, but it's not consistent. So because of that key feature, one thing, what it means is all your data needs to be in one place, right? At the same time, you can't distribute it out. That's the reason why most of these RDBMS, they don't horizontally scale out. But the problem is still there, right? I want to be able to make read efficient and so on. So the typical architecture which RDBMS is used is, they will call as, they will make a copy of the entire data and put it across different nodes. And your nodes will then be able to query it. But it's sharing all or nothing, right? It's not distributing that data across multiple nodes. It will create multiple nodes, and in RDBMS, it will take a copy of all that data and put all the copy of that data on a different node. So they try to sell it saying, oh, we are highly resilient, right? You will not lose your data. Nothing will go down. It will be read efficient and everything. And we support distributed nature because you can create a cluster in an RDBMS, but it's not one and the same thing. Because when you're creating a cluster in an RDBMS and you have the nodes in that cluster, each node, the same data, they will have the entire snapshot of the data. Whereas in a NoSQL database, not all the nodes have all the same data. They have just a part of that data because we partitioned it so that it's query efficient. Remember the 1,000 oranges and one bad oranges? We partitioned it. So each node had those 100 oranges. It didn't have all the 1,000. Whereas in RDBMS, each node has all the data. It has all those 1,000 oranges. So you're creating a cluster, you're creating an entire copy of everything that's there on that one server across all the nodes. Well, then what's the advantage? The advantage is you can have multiple, you can still have the advantage, right? That, you had 1,000 oranges in that one crate. Instead of creating 10 crates and have 10 people do it, what RDBMS does is, no problem, right? I will make copy of those 1,000 oranges, create 10 crates, and I'll have 10 people search for that orange, right? I mean, it's not physical orange, right? It's logical in a way. So they can achieve read performance by making a copy of that data and putting that entire copy of that data in the node in the cluster. So it gets very confusing at times because you can say, well, RDBMSs are also distributed in nature because they create a cluster. No, that's not true. They're creating a cluster, but they're making read-only replicas of the entire copy of that data on those nodes in the cluster so you can achieve read efficiency. Because when I'm running a query, I can run a query across all those nodes, right? I can have one query to do analytical processing. I can have another query to do transactional processing, but I can get some efficiency, but you're still copying that data across all the nodes, right? Because it needs that ACID compliance, whereas NoSQL databases are eventually consistent. Okay. I said a lot and it sounds very confusing and complex, but it takes time to digest it. So any one of you wants to summarize and take a shot at it, because this is confusing and complex, and this is one tripping point. So if I have to find the best architect, and if I ask them these questions, it's very easy to trip on it and lose it. So this is like advanced, but if you understand it, it's not difficult at all. And it takes time as well. So don't worry if it goes above the head, but just try to remember simple things. In a NoSQL distributed cluster, you have multiple nodes. Each node has part of the data, not all the data. Whereas in an RDBMS cluster, each node has all the data, right? So all the nodes, they would have the same data, identical. That way, when you run the query, it's consistent. Whereas in a NoSQL, it's eventually consistent. And that eventual duration is the time it takes to make an exact replica of that data across the nodes, across all the nodes in the cluster. If you can remember that, then it will make it easier for you. I'll take a pause for you to digest and then ask questions And if any one of you can summarize, that'll be great. And if not, I'll be more than glad to explain it 2 or 3 times until this is clear. So what are you thinking? I want to know how you're thinking, because then I can adapt to what you're thinking and explain it accordingly.
Okay, Dr. Mukesh, let me try from my end.
Yeah, that's perfect.
So for for RDBMS, it is just providing that asset compliance transactions is over there, and where we are just using for that OLTP, means online transaction processing is over there as per my things. And for NoSQL, it's providing that distribution manner, and it is highly resilient, and it is providing a guarantee for no data losses over there for NoSQL. If we are if we are if we are accepting for NoSQL environment, so it is providing a resilient data resilient, and replications is also there, as there could be like a number of copies for in different data nodes, means a number of nodes is there. Default is 3 is over there, but in databases it will be only copy will not there, but it will allow read only over there. It is also distributed that one, but it is not allowing for write in another cluster, but it will allow for the multiple read only. And for NoSQL, it is allowed for the OLAP, means online analytical processing kind of things is over there.
Yeah, well, that's really good. Okay. Anyone?
Yeah.
Yes, sorry, go ahead.
Yeah. So mainly the databases are used for the data storage and the query. And we can have an RDBMS where we can store the data and query the data at instance. And we have a cluster of database where we can add more nodes to the into the cluster, which help in the efficiency performance of the database or scalability. And for regarding the RDBS, we can store the data in we have an ACID compliance where we can store the data and retrieve the data with consistency and atomicity. If we can store the data in, suppose we are doing a transaction which is having 3 steps. If one step is failed, so all the thing is rolled back, and nothing is inserted into the database. But if all is completed, then it will go to the database. So it is uh, mm, that shows the atomicity of the database, and it provide the consistency of the data, and it is a work in isolation. Its durability also maintained there. And but in NoSQL database, that is eventually consistent. Suppose we insert some data into database, after certain seconds or minutes, that data is replicated in the different nodes or server in the cluster. And in RDBMS, it is a horizontal scaling. And in RDBMS, generally what we do when that is in cluster, we have to keep the whole the data, or we keep and the same snapshot in the each nodes or each server in that cluster. So that's why we feel that yeah, we keep, and we have a redundant data in each server. But in the NoSQL database, we have a partition of the data in the each server, and yeah, that is what in this NoSQL database. And yeah, that's what. Yeah.
Okay, that's very good. So those who are playing the role of a project manager and tester, you don't have to get into the details and understand the concept, but I'm just throwing your understanding to show why it will help you understand why we are doing certain things. One of the things it will explain you, till today, there are new different types of RDBMSs coming up, and it's trying to solve this problem where they're trying to achieve and combine the benefits of NoSQL, distributed nature of the data, and combine it with RDBMS. So Google is creating new databases like Cloud SQL, which is trying to attempt to do the same thing. So, that's why you'll see new databases are coming up in the market because, it remains a challenge for them. And they want to make sure they're not losing the spaces to these different NoSQL database software providers or software vendors. So that's one of the reason. But if you're a project manager, no one will ask you this question. So you don't have to worry about understanding it in detail. But just keep in mind, these concepts that you heard about it, what's ACID. And I'll send you some links, or I'll try to write this and summarize it for you, because when you have it written, it'll be a lot easier for you. But I don't want to write it first because then you're not going to listen. So I want you to focus on the listening part. Then I will send you some summarized notes. And when you read it and we'll revise it next time, then it will become a lot easier. These concepts, it takes multiple iterations to get that clarity. But once you do it, then it's not that bad. So if you're still feeling overwhelmed, it's very natural, it's normal. Don't worry about it. We'll keep revising it a couple of times. There's something called as a CAP theorem, but we'll do that later on. But this is good enough for now, at least, so that you have a good idea. Okay. The next concept related with this
Mukesh,
is
sir,
yes.
I have a question.
Yes.
If data size is more than cluster size, like 2 GB of data we want to store in NoSQL database, then and cluster size is less than data size, then how it will be stored in that database, NoSQL database?
Yeah. So your size of the data is the combined capacity of the nodes in the cluster. So when you say, my cluster's capacity is, 2 GB, it implies that if I were to store 2 GB of the data, my nodes combine the capacity of the nodes, because not all nodes are storing all the data. They just have part of the data in a NoSQL cluster. So if part of that data, that summation, that combined capacity of the nodes in the cluster is giving your capacity. So if you have more data than your capacity, you don't have an option. You have to add another node in the cluster. And when you are adding another node in the cluster, it's important to remember you're not only going to store that additional data, that new node will also have some copies of the data which other nodes already have it. And that's for the resiliency. Resiliency in the sense that if one node goes down, you're not losing any data. There should not be any data loss. That's one of the fundamental principles, that we should not be losing any data. So when you add, let's say, you want 1 GB more, you just can't add another node for 1 GB and say, okay, added more capacity. That 1 GB will have probably, at least 30% data from other nodes, and then only what is excessive capacity is that capacity. So that's why this adding a node for what is the shortfall is not enough. You have to add more, because it's going to store copies of the other data, and the new data could go on that partition or that node in the cluster. But you'll need to horizontally scale. You will have to add more nodes in the cluster, otherwise it won't work.
Okay, thank you.
Okay, that's a good question. Okay. So we started with this concept that in a RDBMS, you're storing, and in a NoSQL database, you are storing data in the database and you're querying the database. That query engine is also in the database, whether it's an RDBMS or whether it's a NoSQL. As the amount of data grows for RDBMS, your sizes of the nodes in the cluster, they will have to get bigger, right? Because that's how RDBMS works. It copies all the data across all the nodes. In a NoSQL, you will have to horizontally scale out as well. Okay. For RDBMS, it becomes a problem because a lot of the companies, they already have RDBMSs, right? They didn't invest in a NoSQL. They already have relational data. And they've got their systems which is capturing that data and everything. So scalability becomes a problem because you have to buy bigger and bigger boxes, right? Nowadays we virtualize them. So physical, previously, I'm going back in time, virtualization came like 2005, 2010, that time frame. Before that, there was no such thing as virtualization. You would install the database software, we call it as on the bare metal, the physical server. You would actually install, you would have an admin and they would install that database software on that server, right? And then when virtualized machines came in, you would install it on the virtualized machine because it's easier to scale, add more CPU cores, and allocate more RAM and memory to a virtual machine. Whereas in a physical machine, you have to take out that RAM card, that it's a chip, and you have to physically put another one. Whereas in a virtual machine, it's a lot easier to do that. So that's why pretty much it's a standard. No one will install it on the bare metal or on a physical machine. They will use VM for it. So the problem, because my query engine and my data storage are on the same server, as the data grows, right, of that server, I'm adding more CPU and RAM to it. Even if I just want this space, I'm adding more CPU and RAM to it because, I need to make sure I need to be able to process it. Is that a problem, or why do you think that is a problem?
Can you explain the question again?
As we are adding more and more data storage to a server, right? And I'm in an RDBMS. Let's take the example of RDBMS. As the amount of data keeps growing, because I'm storing the data in the database and everything is in one place, the SQL query engine and the data storage, it's all on one machine. As I add more data, I have to get a bigger machine. So I not only need more disk space, but when I get a bigger machine means more CPU, more RAM, more disk space. Is that a problem, or why that could be a problem?
It could potentially cause a conflict or slowdown of your search because it's trying to write the data and access it at the same time. So it could slow down the process.
Yeah, that's one reason. But there's another. So what's happening is, because your query engine and your data storage are tightly coupled or in the same place, as your data scales, your data is growing, you're adding more CPU and memory to it. But your queries, they are depending on your use case. You may not be using all that data. You need it for analytical purpose or anything, or you're pushing that data somewhere else. So your query computational is not growing exponentially as the growth of your data. But because you're vertically scaling, both your computational power and your storage power, they are growing together because they are on the same machine, right? So if everything is on the same machine, as your data grows and you're getting a bigger machine, you'll get more CPU and RAM. So you are increasing your computational power. But even if you don't need your computational power, you're still increasing it. Does that make sense? So let's take an example. I've got a server which has 100 cores and it has 1 terabyte on my database, RDBMS. Let's say MySQL. I've added a new business capability, right? In our retail company, let's say I'm adding few more products. And in that case, I'm expecting more transactional value because now I'm selling more products. People will be able to buy more products from my website. So I added more products. I'm expecting a growth in business and more transactions. People are placing more orders and there's a transaction for it. business is saying, well, make sure this website is functional and everything is good, and my orders are processing and everything as well. And say, make sure, there are no problems with it. You as a data architect, you look at the database and say, well, I've got 100 CPU cores, 1 TB RAM or whatever that RAM is, and 1 TB disk space, sorry, and we said 128 GB RAM. It's good enough for now, but considering the growth and everything, I'm expecting a lot more transactions, right? The order processing is, I just have to run a query saying, okay, which orders do I need to ship? But my writes are going to be far exceeding the number of reads, let's say. I'm just making a hypothetical example on the fly. So I'm writing a lot more data to the database. And then there's a downstream process where someone is actually shipping the order. So now I need to add more disk space storage to my database server. And given that I'm already at 80 to 90% of my existing capacity for my server, and I've already used all the hardware drives maximum that I can attach to my database server, I have to, because I'm using an RDBMS, I have to get a bigger server, which means I have to pay more for it, even though I just need capacity, more disk space capacity, because my CPU utilization is at 20%. So even if I'm adding more disk space, it will go up, maybe the CPU utilization will go maybe 40%, 60%. But I've got enough CPU, I've got enough memory to process those additional handles, those additional transactions. It's just the disk space that I need more. But because I need to scale, and my disk space and my query engine both are on that same server, I've already had capacity of my disk space. I have to get a new server, whether virtual machine or physical, but it has more of CPUs and it has more RAM and disk space. I really didn't need that additional CPU and RAM, because my problem was that I'm at capacity for the disk, how much disk space that server has. But I still got additional CPU and RAM just because I had to add that storage. And that is a problem, because I'm unnecessarily spending money. Business has a problem. So I'm unnecessarily spending money on that additional server, whereas I only wanted to spend money on that storage. So the problem statement is, my data storage capacity is growing. There's no need for my computational capacity to grow. But when I'm vertically scaling, both are growing at the same time. My computational capacity is growing, my storage capacity is growing, but I needed only one of them to grow. Tightly coupled together, they're both linked with each other, and they're on that same server. Both grow together when I add more capacity. Similarly, when I need more computational power, the storage is the same. I'm going to get another machine which will have capacity for a lot more disk space, and it will come with a bigger drive as well. Even though I didn't need it, I have a lot of bigger drive as well. So you might say, well, disk space, extra disk space is okay. Why does it matter? In this simple use case, it doesn't make much of a difference. But when you're talking about large companies which have terabytes, zettabytes of data, and they've got a lot of computational, there is a need to separate and de-link the growth of the data storage from the growth of the computational power that is needed. We need to separate the two, because in a database, the databases were designed where you store the data in it and you query it. Both that capacity to store the data and query the data is a functionality of the database software. We need capability to separate the two. And this capability becomes more important and easy to recognize when we start talking about big data, because you've got data from multiple databases. Now you need to store it in one place and process it as well. So your data is also growing, your computation is growing, but they don't grow at the same time. It grows, sometimes you have more data, sometimes you have less computational powers. With analytics workload, you have the same amount of data. Everything was working fine, but now someone joins and says, I want to do AI ML. You need a lot more computational power. And just for that lot more computational power, you have to get more servers. and those servers come with disk space, which you really didn't need it, but you're still investing in it. So there is a need to delineate computational power from storage power. And that concept gives rises where you can separate out the query engine, right? And separate out the disk storage. And this concept it confuses so many people because they're not used to that. Because if you tell that to a database administrator saying, can you run a SQL query on this file? They'll be like, are you crazy? You're running a SQL query on a file. I need that data in a database. I can run SQL query on a database. I can't run SQL query on a file. I can't run a SQL query on a CSV or an Excel file. You can't do that. You have to load the data from an Excel into the database, and then you can run that SQL query. But I'm asking, I've got a lot of files. I don't want to put that data, make a copy of that data in the database and then run query for it. Can you run a query, a SQL query for my files, which are stored in this location? Can you do that? If you ask this question 5 years back, they'll think you're crazy. Nowadays, that's the smartest way to do it, is where you are able to query your data on data which is in files, but that data is not in a database, right? This creates a new concept which we call as decoupling the query engine and decoupling your data. So if you're going to store your data as files and not load it in a database, there are new different types of file formats which are coming in place, which allow you to run a serverless SQL, or you're running a SQL engine, or you're running a SQL query in memory, which will point to those files and run the query, right? So this concept is so new and it's so exciting that organizations, they want to be able to do that, where they've got that elasticity, where if you want more computational power, sure, increase the computational power. If you want more disk space, just add more disk space. You're not tightly coupling both of them together. Okay. So that's why you find new file formats which support that running the SQL query on that file. Examples of those file formats are Parquet, P-A-R-Q-U-E-T. So a .parquet file, a .delta file, .arrow files, and now more and more files are being supported, the file types. But that essentially brought a need for creating different type of files, file extension, so it can efficiently store that data so that it can be queried by a query engine. But that query engine is not a database, right? Because it's not storing data. It's just a query engine. So nowadays you have separate query engine, which will take that data, load it into memory, run the query, SQL query on that data in memory, and then write it back to a file. But it didn't store a copy of the data in a database, which means it makes it a lot easier. You don't have to store that Excel into the database, load it, and then run a query. You simplified the operations and you got that elasticity. And that's very much desired by companies where, you want more computational power? Sure, no problem. Use a query engine and you'll pay for it as you go, or pay how much as you use. And Apache Spark does that. And most of the data warehouses, Amazon is offering the same thing, Google is offering the same thing. But serverless SQL is that concept where you have a query engine and you can use that query engine to run SQL queries on data which is not in a database, but that data is stored as files on some server. Does this concept make sense?
Dr. Mukesh, concept is fine, but if you think out large enterprise data, large data is there for a growing company with multiple businesses and all. So how come, this all that data come into a in file and then it's buried in memory?
Yeah, it's a very good question. So probably in the next session, we'll cover more of the life cycle. How is data growing? how is data, why and how data is being consolidated on the data lake? Because that brings the concept of what is a data lake? Why do we need a data lake? Why is it called a data lake? And why do we need to consolidate all the data in a data lake? And what is the strategy? So this would be perfect for us to answer this question in the next session, because I'll need at least an hour to explain that. So next week's agenda, we'll cover this concept. Why are we storing this data? Where are these files coming from? And what's happening? We'll cover that. Any other questions?
Yeah, Mukesh, anyhow, we are covering this file type in next session, but still I want
Yes.
to understand means in a streamline environment, we are pushing the data to we are pushing data to consumer side, right? So means
Yeah.
what would be format means and that is the streaming data is over there. So it
Yeah.
could
So
not be
data
like
consumer, just to be specified, right? Here, consumer is nothing but a data consumer. Example of a data consumer could be Tableau reporting or using any reporting tool using Power BI or doing descriptive analytics. An example consumer is using analytic workload where you're doing AI machine learning. That could be another consumer of data which needs a lot of computational power if you're using deep learning or so on. A third different type of consumer is you want to expose that data as an API or as a service so you can share that data with other systems. So you'll have multiple consumers of that data. So how to efficiently store that data so multiple consumers can consume that data, and each consumer is writing its own SQL queries. So each consumer has its own computational workload for using that data.
okay. So one more question, sorry. So directly we are consuming the data from our various data sources. So again, all this means a data pipeline on production, or we are just consuming data in our staging environment and then we are transporting that on our production. So I just wanted to understand.
Yeah, so anytime we want to run all this in production, but before we run it in production, we want to test all this. Your queries is running fine, your queries are working fine, and so on. So usually, any project, sorry, any project before it goes into production, you will test it out in the lower environments with some sample data, or sometimes we use what's called as pseudo anonymized data which looks like real world but is not the actual patient data, because there are a lot of data privacy laws, especially when it comes to healthcare. I just can't use any person's data, put it in a lower environment and use it for testing, because I'm violating the laws which says I cannot do that. So, but yes, everything that needs to happen and tested in the lower environments.
Okay.
Yeah.
Okay. Thank you.
Okay. Who wants to summarize just two concepts? We primarily covered two concepts today, and rest we are revising. So who wants to summarize it? Right, wrong doesn't matter. The fact that you're attempting to it, you will see the benefit, and you can tell us next time if you benefited by summarizing it.
Yeah, I think I have summarized the first part, like regarding the clustered server about horizontal scaling and vertical scaling.
Yeah.
Yeah, so first thing I'll summarize. First, we have talked about SQL RDBMS database, that is a table structure and data. It is having a row and column format. For NoSQL database depends on it is not schema less, and it depends on query, and it is yeah, and there we have talked about the streaming of data, and the streaming of data is depends upon the creating data using some sensor like ECG, live data like weather data, stock market. On that streaming data is changing every time, and here the producer is pushing the data to the consumer. and consumer need to subscribe to that channel or to get that data. And we have talked about previously we have talked we are more focused on the efficiency of the database, but nowadays it is about the performance of the database. And mainly in database, for two things happens. There's the data storage and how we're storing the data and how we are querying the data from the database. And we have talked about the RDBMS database, and we talked about the clustered of the different clustered things, that is have different server, where we are having the group of server, and each mm, mm, might be a virtual machine or it is a physical machine, and each machine is known as the nodes on that clustered database or server. And we talked about like vertical scaling and horizontal scaling. And it is in vertical scaling, it is example is Burj Khalifa, where we can have multiple server, but before designing that type of scaling, we have to define how much it is having some limitation, and it should have some foundation part. And after that, some point of time, we can't scale it. Like here, we can increase the RAM, but in certain point of time, we can't do that. But in horizontal scaling, we can increase the server depending upon your demand. So where we can use the cheap hardware, and suppose in current point of time we don't need much server in that system, uh, and then incrementally we can add the server in that framework actually. So horizontal scaling is more reliable. And yeah, scalability, we have talked about the RDBMS is the horizontal supports the horizontal scaling, and there we can have multiple server and server in the cluster. There we keep the data. We have a snapshot of data, same data in the each node of that clustered system. And RDBMS have an ACID compliance. Their ACID stands for A for atomicity, C for consistency, E for isolation, and D for durability. That means that suppose you are doing some transaction and it is having 3 steps. If one of the steps is failed, then it roll back that whole process, and it maintains the atomicity of that system, and it provides the consistency of the data. So each time anyone query to the same data, it will get the same result. And whereas the NoSQL database, it is provides the eventually consistency, because suppose you create a data to that NoSQL database, after some time, some so 1 or 2 seconds, it pushes the data to different nodes actually, and it is partition based actually. All the data is not available in the same node. It is splitted to the all the nodes in that cluster system. And we have talked about nowadays we can have RDBMS is decoupling of data. We can have a SQL query engine. There we don't need to connect to the RDBMS or database. We can keep the data in the flat file in our machine, and we can have the SQL query engine, and and by that we can that will load the data in the memory, and it will point to the .park or delta file which having the data, and query the data from that file. Yeah, that's it. I have some.
No, that's very good. Were you saying this from memory or you actually took notes?
I have notes.
Okay, okay. Next time when we summarize, I want you to tell from memory. Can you do
Yeah,
that?
yeah. Yeah, actually, I have a memory technique, mind mapping, that is PEG system. I'm not using that. I know that, but right now I can use it.
Because think of it this way, right? You're giving an interview, so more interviews nowadays are video interviews, so you cannot read the note. So correctly, but I want you to be able to, save all this, pretty much what you said, from your memory. So you stored all this in your notes, your data storage is on the notes, but I want this to be an in-memory. So you're storing it in memory and then you are saying it out of in-memory. So if you can do that, and I want all of you to be able to do that, because then no tension, no stress when giving interviews, because it's there in your memory.
Yeah, I could. Yeah, thank you.
Okay, well, awesome. Thank you. We'll conclude our session with another mind empowerment technique. So we started with the mind empowerment techniques so that, we are avoiding wastage of thoughts. And we said we don't want to involve ourselves in situations where we can't make any difference. But even if we can't make a difference, we can always make differences that are not visible. They're very subtle. You can't see it. You don't even know if it makes a difference or not. And that difference is by giving good wishes. Another technique to avoid wastage is putting full stop to the questions. We covered this in the previous session, but it's important that you observe it and you apply. Many times we get a lot of these questions, and the most common question is after something has happened, there are too many questions. Why it happened? It shouldn't have happened to me. Why does it always keep happening to me? And that one question brings a hurricane of multiple times, and it will drain you. And previous week we covered, right? That causes stress as well. When you have too many thoughts per second that you cannot process, in simple words, in English language, we call saying, I'm feeling stress. So we want to regulate those thoughts. And any of those thoughts that are related with the past, just put a full stop to it. We cannot past. We cannot change the past. We can certainly take lessons from it. But if we take the lessons from it, learn from it, then repeating that same past is not going to change anything. You already learned the lesson from it. But yet many times we drift in the past and we replay it in our mind. And that wastes a lot of time and energy. We covered this in one of the mind empowerment, but I'm repeating it again to make sure that you are applying it, and you will notice a difference in how efficient you are, because a lot of the time, just observe your mind. Leakage of time and energy. The past, put a full stop to it. Move on. You need to look forward, right? We also covered in the mind empowerment technique being a witness. Many times people ask questions, what does God do when our war is happening in Ukraine and war happening in Israel? What does God do? Where is God? What is God's role? Well, God is playing the perfect role. He is the perfect example of a perfect witness. He is witnessing everything. He doesn't interfere and say, okay, Russia, you stop, Ukraine, you stop, US, you stop, Israel, you stop. He doesn't interfere in it. Why? Because this is a scripted drama and it's perfectly written. We associate perfection with God, right? Because we say, except for God, nothing else is perfect. This is a scripted drama where everything that happens for the best. We cannot see the best right now because we say people are dying, this is not right. We've got our opinions. These opinions are also a waste of time. Our opinions don't make difference. What makes a difference is best wishes. So in this perfectly scripted drama, war is part of it, right? So there are going to be more wars as well. That is known, and we know it is part of the drama, and it's perfectly scripted. By questioning it and wasting our time and energy where we cannot make any difference, it's a waste of time as well. God himself is a witness because it's perfectly written. What is the benefit of it? He's explained to us, but those who don't know the benefit don't understand it, and then they question it and they waste their time and energy because they don't know what happens after that. But God is, like in Hindi, we say Trikaldarshi. He knows the past, he knows the present, he knows the future. The future is a lot brighter. So this is just part of the play. So don't waste your time and energy thinking what's going to happen. Is there going to be an India and China war? Is there going to be a Taiwanese war? All that is a waste of time. That is God's work. That the script is perfect. It's exactly how it's supposed to be. Your role in it is give the best wishes. What God does, he plays the role of a perfect witness, and he's constantly giving good wishes for the souls to overcome all the grief and the mountains of grief that are yet to come. This is just the trailer. This is the beginning. So he's equipped us with all the knowledge, with all the spiritual powers, with all the strength to be able to withstand it, because there's something that will come better after that, right? So be a witness just like God is, but you can't, if someone is dying on the road and he goes, well, I'm just being a witness. Come, power of your best wishes. Things that you can make a difference and do, certainly do it. But if it's beyond your role, it's outside, that's something that you cannot do, be a witness and give best wishes. Giving best wishes, you can always do that no matter what your situation is. So the combination of perfect witness and giving best wishes will not only bring the best in you, but will also help us make a better society. So with that, we'll conclude the session for today. Any questions, feel free to drop it in the Python group. Sorry, not Python group, but in the group as well. I was thinking about that. But feel free to write your questions in that data architecture group. Do install the database software. This time when you install it, you will see, it will ask you, is it a single node installation or is it a multiple node installation? So this way it will make sense, because you know it's a cluster, but because you're installing it on one node, it will be a standalone. But if you were to install in a real world, it will ask you, is this one of the nodes in the cluster? And it has different configurations for that. So please do install the database software. So next week we will cover out the, so that way it will make sense. With that, I wish you a very happy productive week. Thank you.
Thank you.
Thanks.
Thank you.
Shanti. Thanks, Mukesh bhai, and thanks everybody for joining and helping us up to learn about the data. And I will end the session here, and we'll meet next week.
Thank you, all of you.
Thanks. Bye-bye.
Thank you all.